Today, we'll be doing a little bit more practice on some of the concepts that we've been learning in our previous videos, specifically on circuits and circuit theory. We've covered different aspects of resistors within circuits, electric fields, capacitors. However, now I think it's time to really put everything together and look at a couple more practice problems. So we'll be looking at 5 specific practice problems, and these will be things that are really used in everyday applications and can be seen in a lot of y'all's AP exams as well as engineering exams as well. So without further ado, let's jump into our 5 practice problems. Now here's our first one. We have a word problem in this case. We have R1 equals 5 ohms and R2 is 10 ohms, and these two resistors are in parallel. That combination is in series with R3, which is equal to 4 ohms, and R4, which is equal to 6 ohms. What is the total resistance of this entire resistor network? So with any type of resistor problem, we need to translate the wording of the question into an actual circuit diagram, and that's exactly what we're about to do right now. So in this case, make sure my pen is up. We know that we have R1 and R2 in parallel. So let's draw a parallel resistor network. We have R1 up here, R2 up here. Here's your parallel resistor network. Now we know that this combination is in series with 2 series resistors, specifically R3 and R4. We know this is R3. And now we know this is R4. In this case, as with a lot of circuit diagrams, we normally have some sort of voltage source, but we don't really need that in this case, since all we're really calculating is the total resistance. In this case, our main strategy is going to be to, first of all, combine the parallel resistors. And the second thing is to add the parallel resistance that we calculated in step 1 to the series resistance R3 plus R4. So let's do specifically that. We can solve this problem in 2 quick steps. So we need to first calculate the parallel resistance, meaning 1 over R12 is equal to 1 over 5 plus 1 over 10, which is equal to 3 over 10. This means that R12 is going to be equal to 10/3, or approximately 3.33 ohms. Now, this is a very important value because that is the equivalent resistance of this parallel network right here. However, we're not done in this case. We still need to add R3 and R4 into this network, which leads me to step 2, which is add series resistance. So in this case, we would do R12 plus R3 plus R4 is going to be equal to R total, meaning this is going to be 3.33 plus 4 ohms plus 6 ohms, meaning that our total is going to be equal to 13.33 ohms, which is our final answer. So not bad. This is a pretty simple sort of question that anybody could get in a simple physics or circuits exam. And is a pretty common example that kind of comes up, especially with respect to combination circuits being series, parallel, some sort of mismatch of that. So with that said, let's go to problem number 2. Get a little bit more challenging in this case. So here, unlike the last question, we have only a circuit diagram. We have no more words. In this case, just by looking at the question, looks like we have a 24-volt battery, or a voltage source, and then we have 2 parallel resistors in pair or in series with a series resistance. That would be R1, the series resistors, and then this blob of R2 and R3 being the parallel resistances. What we need to specifically find, though, is this value, the current that goes through R3, meaning this branch is the current that we need to find specifically only in R3. So once again, we can solve this in a couple of simple steps. Like the previous problem, we simply just need to break down our equation or our circuits. So first, like last time, find the R equivalent parallel resistance. That equivalent parallel resistance is going to be 1 over R23, which is 1 over 6, plus 1 over 3, which is going to be equal to 3 over 6, which is going to be 0.5 ohms, meaning that R23 is going to be equal to 2 ohms. This is going to be an important example because it is that parallel resistance. Now, we just calculate the total resistance, total R. That is going to be R23 plus R1, which is 4 plus 2 is 6 ohms that we've calculated. Now we can plug and chug this into Ohm's law. What we don't know in this case, since we have the voltage of the circuit and we have the total resistance, all we need to do is simply solve for the total current within the circuit, meaning step 3, Ohm's law is going to be I equals V over R. Solving for this is going to be 24 volts over 6 ohms, getting a value of 4 amps total in the circuit. Now this 4 amps is going to be distributed to a variety of different circuits, whether it goes through one branch or another, and that's specifically what we need to find out in this case. What we know in this case is that the voltage across R3 is going to be equal to the voltage across the parallel branch, which is 24 volts, minus the voltage across this R1. So if we take this 24 volts minus the voltage drop across R1, we will get the total voltage drop across this entire parallel resistor network. The way we calculate that is by simply doing VR1 is equal to 4 amps times 4 ohms is equal to 16 volts of voltage drop across R1. This is a simple Ohm's law equation that we use because V equals I times R, which is equal to voltage once again. Therefore, as we said before, V parallel is therefore going to be 24 volts minus 16 volts, giving us 8 volts parallel across both R2 and R3. We know that there's 8 volts across both the 6 ohm resistor and the 3 ohm resistor. Now, in this case, we pretty much have everything that we need. We know that R3 has 8 volts across it. We know that R3 is a value of 3 ohms. Again, we can plug and chug this into Ohm's law. We have point number 5. Current IR3. That is going to be equal to 8 volts, the same value that we calculated previously, over 3 ohms, giving us a value of 2.67 amps, which is our final answer. So this problem was significantly more in-depth and involved, but by breaking it down step by step and understanding simple rules of both parallel and series resistances, it's a pretty simple problem that we can solve by iteratively using Ohm's law over and over again. Let's move on to another question. Question number 3, power dissipated by one resistor in parallel. Again, like the past problem, we have just a simple circuit diagram. In this case, what we have is a 12-volt battery or a 12-volt power source attached to 3 parallel resistors, R1 being 2 ohms, R2 being 4 ohms, and R3 being 6 ohms. we need to find the power dissipated only by R2, meaning we need to find the power just right there. We can go through some of our power equations. The most relevant power equation that we're going to use in this case is going to be P equals V squared over R. This is the equation that we're going to use to eventually solve this question. For R2, in this case, since we have the resistance, that being 4 ohms, all we need to do is deduce the voltage across that resistor. However, since we know that the voltage across these parallel branches is going to be equal, we know that the voltage across R2 specifically is going to be this given 12 volts value right here. So this turns into a pretty simple plug and chug type problem. We know that power is equal to V squared over R, meaning that we have 12 volts squared over 4 ohms. This gives us 144 over 4, providing an answer of 36 watts. So a lot easier in this case. This is a one-step problem, but again, understanding the series and parallel resistor rules when it comes to current and voltage is super important when actually applying some of these equations. Let's go to the next problem. Problem number 4, home stretch. In this case, we have a bit of a different problem. We covered capacitors in a previous video, and capacitors happens to be a pretty challenging example of how to actually calculate the total capacitance. When we calculate the total capacitance, the rules that we calculate with respect to the resistances are completely flipped. When you calculate parallel capacitors, the equivalent capacitances are going to add up. Versus if they're series capacitances, we use the reciprocal rule like how we used with parallel resistors. Let's apply that concept in problem number 4 here. In this case, we have 3 capacitors, capacitor 1 being 8 microfarads, capacitor 2 being 4 microfarads, and capacitor 3 being 6 microfarads. All we need to do is simply find the total capacitance of the equation. So, as I mentioned before, we first need to combine the series capacitances, meaning a equivalent capacitance of this branch right here, and then combine that with the parallel branch C3, turning into about a 2-step problem. So, let's deduce what our answer is. Step 1, combine series capacitors. This is going to look like 1 over C12 is equal to 1 over 8 plus 1 over 4 is equal to 3 over 8, meaning C12 will be equal to 8 over 3, or roughly 2.67 microfarads. Now, this C12 value corresponds only to the parallel section of the series, or only corresponds to the series section of this whole parallel capacitor network. That leads us into step number 2, meaning finding the total capacitance. By far the easiest step of this question, C total will be equal to C12 plus C3 equals 2.67 plus 6 gives us a value of 8.67 microfarads, which is the equivalent capacitance of the entire capacitor network. So once again, once we keep in mind that these resistor and capacitor rules are flipped, such that the way to calculate parallel resistances is the same as calculating series capacitors, and calculate series resistances is the same as calculating parallel capacitors, the problem becomes pretty straightforward, and all we do is really apply the rules. Finally, problem number 5. We're going to use a voltage divider in this case. Let's go back to doing some word problems here. We have a voltage divider circuit with V in equals 8 volts and R1 equals 3 ohms and R2 equals 9 ohms. Find the voltage across R2. So this is a pretty interesting problem. We first of all need to know what a voltage divider circuit is. If we need a little bit of a refresher, a voltage divider circuit is simply a circuit that literally divides the voltage of the input voltage. So that input voltage being divided is going to be this 18 volts. As we recall, if we have suppose we have parallel resistors. Parallel resistors are not going to divide voltage since the voltage across each parallel branch is exactly the same. Therefore, this resistor, this voltage divider circuit must be a series circuit. Therefore, let's draw it and see what happens. In this case, we have a 18 volt battery supply that is connected to a resistor, another resistor, and we complete the circuit. R1, R2. Now we need to just find the voltage across R2. Pretty easy in this case. Let's first write down the voltage divider equation. The voltage divider equation, VR2, is going to be equal to Vin multiplied by R2 over R1 plus R2. In this case, all we have is the equation. We simply need to plug and chug and we get our final answer. Therefore, VR2 is equal to 18 9 ohms over 9 plus 3. And this simplifies to 13.5 volts is our final answer, meaning there's 13.5 volts specifically across R2. So this is a pretty easy example. And if we are creating some sort of application where we need 13.5 volts specifically from an 18 volt battery, this is a sort of circuit that we would need to create that 13.5 volts. So once again, we've gone over 5 examples. If you are looking for more practice or want more tutoring on physics E&N, visit us at voltagelearning.com. And don't forget to like, comment, subscribe to more YouTube content. Until next time, we'll see you guys later.